welcome to the FRC programming class. This week we'll be covering sensors and controllers. So first off, I want to give a quick introduction to the class. This is the first lesson. So we have two instructors, me and Matali, and we'll be switching off every week who's teaching which class. So the class will focus not on how to necessarily write the code, but instead of like how the code kind of works itself. And then we'll still cover a little bit of the Java code in the classes, but most of the Java code will be in the assignments they can learn. The class timeline will cover sensor controllers, PID, state machines, vision, autonomous, GitHub, and configuring your electronics. It's 6 weeks long, and the first lesson we have today is focusing more on kind of some electrical stuff and less programming, but the other classes are more heavily focused on programming. Okay, so sensors. What is a sensor? So a sensor, in FRC terms at least, is just something that'll read things from the real world and translate that into electrical signals. And this is super useful because you can use this to detect game objects, the position of mechanisms, the angle of the robot, etc. And we can use all this data to more effectively control a robot. So sensors allow us to have a more accurate autonomous, more accurately move an elevator up and down, or more accurately move an arm forward and back. So sensors, as I said, transmit their data through electrical signals. And so most sensors change voltage depending on what's happening, what the sensor is reading. So voltage is a change in electrical potential in motors, and in motors, it's changing the voltage provides a change in the speed of the motor. And that's just kind of for reference and for future. And the voltage range for most sensors is going to be 0 to 5 volts. And sometimes in FRC you might see a 0 to 12 volt sensor, but it's less common. And sensors can transmit through many different ways. The main two are analog, which is variable voltage, anywhere from 0 volts to 5 volts or 12 volts if it's a 12 volt sensor. So you can have like 2.5 volts anywhere in between. Or you can have digital signals, which are binary voltage, means it's this or that. So if it's a 5 volt sensor, it's 0 or 5 volts. Or if it's a 12 volt sensor, it's 0 or 12 volts. Nothing in between. Okay, so how do sensors collect? So the sensors collect the data and send electrical signals over a wire. How does our code access that? So most commonly, the RoboRio will just directly have a sensor plugged into it, and you can read data like that. Sometimes you might also have a sensor plugged into a motor controller, which is then hooked up through the CAN bus into the RoboRio. So through the RoboRio, it can be plugged in through a couple different ways. The most common are the digital input-output, which means the RoboRio can take an input of a digital signal and read it through code, or it can output a digital signal, which is a little bit less useful. Analog input means it can only read from analog sensors. It can't actually output analog, which is fine because that's really all you'll need. There's also a couple others. There's PWM, and PWM is basically, it's a digital signal. It can input and output that digital signal, but instead of a normal digital signal, instead of what it is it's a digital signal that acts as an analog signal. So it goes back and forth between minimum voltage and maximum voltage really quickly, and the rate at which it switches back and forth is that analog value. If that makes sense. It's a little bit easier electrically to make than an actual analog signal, and so that's why it's a little more common. There's also I2C, which you might find maybe a LiDAR or something has an I2C. Now, for FRC, they should provide you with example code or libraries themselves, but you might end up having to write your own code if it's not really a device made for FRC. There's also serial, which is less common, for sensors at least. There's the RS-232 port right here, and there's also the SPI port right here, and the two USB ports. Now, the USB ports are super common for cameras, but we're not going to call cameras as sensors, even though they technically are. It's not many devices in FRC transmit so much data that you would need a serial port, so it's definitely less common. There's also the MXP port, and it basically has a bunch of different types of ports. It has some digital input-output, analog inputs, etc. And so you might have a device that covers up the whole MXP port to use. So there's like the Navex MXP which is a gyro that you can stick into the MXP port, and it also has some other things it has on there. And that's just super easy to hook up. Something for that, you probably don't want to be writing your own code because it's probably going to be super complicated. And so, like the NavX MXP has its own libraries that you can use. Okay, so how does your code actually get this sensor data? So, for anything with the RoboRio, you're usually going to be using WPI-lib. So you might have to use Kawaii Labs' libraries, for example, if you're using that NavX MXP, even though it's plugged into the RoboRio. But like every other single port on here is using WPI-lib. This is the default libraries for RoboRio, and it basically runs everything from the driver station to the controllers, etc. And so, to read from a digital sensor, the one line of code you'll definitely need is you make a digital input object, you name it whatever you want, and then you say what port it is. So these are the port numbers on here from 0 to 9, and 0 to 3 on the analog. Then this get function you can call later in your code just returns true or false, a boolean, whether the voltage is 0 or 5 volts. Now, I didn't mention before, but all of these ports in here are all 0 or 5 volts. 0 to 5 volts. Nothing here is 12 volts. You can plug in a 12 volt, like digital sensor. I don't recommend it, but like worst case, you could plug in a 12 volt digital sensor into here, and it'll still read it just because it kind of it kind of works, but it's definitely not ideal. Analog's a little bit more complicated. How that works is you create the analog input just like the digital input, and you specify the port. The difference is there's a bunch of different formats or ranges of numbers that the sensor will return. So you can return like get voltage, and let's say we have a pressure sensor where 0 psi is the minimum and 5 volts on the sensor is like 132 psi or something weird like that. You would have to like get the voltage divided by 5 and then times 132 to get your actual range and your units to psi. There's also a couple other functions like built in, like get value, which I think just gives you percent just divided by 5 automatically. Not totally sure on that though. PWM is a little bit the same as the digital, or sorry, the analog, but the difference is they have some more built-in stuff to work better with encoders. So this get position method in here, it'll every single loop it'll continuously add up the value or the change over time, and then give you the get position if that's useful for encoders. And also, just a quick example: if you plug in a limit switch, or you plug in a encoder into a Talon SRX or a Talon FX. You can also do it for like a Spark Max or something. For a Talon, what you do is you create the Talon object like normal, and then you can control your motor however you want. And then for an encoder, you just do Talon.get selected sensor position. For limit switches, there's a couple more functions, but it's just kind of you use different libraries. So the code looks a little bit different. Okay, I'm going to give you some examples of sensors, how they hook up, and then how you access them in code. So this is a super simple 5-volt Hall sensor, and if you don't know what a Hall sensor is, it's basically a sensor that detects if a magnet is in range of it. And so we love this sensor because it's pretty reliable. You just simply plug it into the DIO port on the RoboRio, or you can also do some wiring and hook it up into a motor controller. And the nice thing about this sensor is this blue LED turns on when the magnet's in range. So that's super useful. So let's say we have a limit switch that's at the bottom of an elevator, and I want to make sure the limit switch is working before the match. I just look down and I see a blue LED, and I know it's wired correctly. You don't have to use a voltmeter or anything. You just automatically know, okay, it's working. It's also super simple to wire, and that's why I like it. Another one that's super nice to have, if you do use CTRE devices, that is a Pigeon IMU. It's a super small gyro. This thing's like maybe an inch long or a little bit bigger. You can hook it up with this port right here into a motor controller, like a Talon SRX directly, or you can run over CAN, and that's super simple also. This one only hooks up to a Town SRX, and it's a uh, mag encoder. Basically, how that works is you have this magnet right here spinning on a shaft, and then you put this motor above the shaft, and it looks at how the magnet spins and then counts over time, and you can detect the position of an arm or an elevator, etc. The nice thing about it is it's super accurate. If you're using a Talon SRX, it's super simple to wire. They also have a version of this in CAN, so you don't actually need the Talon SRX, which is super awesome. And we use this a lot. We used it more last year and less this year because we use the encoders that are built in to the brushless motors. Now this is basically the same thing. It's literally the same encoder but kind of flipped sideways and put vertical. And so this port's right there if you can't see it. And you can hook it up into... This doesn't support CAN. This only supports plugging directly into a Town SRX. But this is a versaplanetary slice. If you know what a versaplanetary is from Vex Pro, you just put in a little slice and it can detect the position. This is super simple on low torque mechanisms. So, like for example, our control panel mechanism had this detected. There's not much force against it, and so it's super good. The thing about like versaplanetary things and other sorts is this gear right here can shred if you're under high torque. So I don't recommend it for like an elevator or a big arm like to climb. These are some sensors that are super useful. These are both photoelectric sensors, and so basically they're kind of like the Hall sensor, but they're all light based. And again, they have this LED on top. They also have one for power and one for if the signal's true or false. The reason they're super nice is they're really easy to mount, and I mean, they are a little bit expensive, but they last forever and they're super reliable. I've never had a single issue with a banner sensor since we've used them. And they come in so many different versions. Like this just sensor housing probably has like 300 versions of it, so you can find it for exact case you want. This one specifically, it shines out a light to 50 millimeters that then bounces back to it. And this is super useful for detecting things like a hatch panel in 2019. If the hatch panel was just close, it just triggered. Or in 2020, we used it sideways in our hopper to detect when the hopper was full or when it got a ball in to start. This one is a little bit different. We used this in 2019. This shines across, and instead of just automatically coming back at a certain distance, this goes until it hits the retroreflective panel, and then it bounces back, so you can have a little bit longer distance with this and adjustable. Okay. Next, we're going to be covering controllers. So how the RoboRio gets the data. So first off, you start out with a controller or multiple controllers or a joystick or things like that. Those plug in through USB into your laptop, which is the driver station, which then transmit a signal over Wi-Fi into the radio, over Ethernet, and then into the RoboRio finally. So this whole process is happening constantly at 50 Hertz or every 20 milliseconds. But there is a little bit of delay, especially here over Wi-Fi, so you might find that at competition, your controller is a little bit more delay, and that's something you should account for. So how your code gets this data. So again, since it's the RoboRio, it's WPILib, and so there's two classes. There's actually a couple more that I'm not mentioning here because they're not super useful. There's the Xbox controller and the joystick class. And so the Xbox controller, you just make an Xbox controller object and you plug in the port, and that port number is 0 through like 6 or something, and it's based on what order you plugged in your controllers. And this is something you need to account for, because if you have one controller for one driver, one controller for the other, you need to make sure you plug it in the same order. You can actually check which number is on which on the driver station, because you could have your operator or your driver swap, like have the same controller but plugged in different orders, and now they're using different controls. Definitely something to account for. And once you've made the object super simple, you can do controller.getAbutton.getButton, etc. Or you could do controller.get Y, which will return you the Y axis. Then there's the joystick class, which is the same thing, but you can use like get raw button methods, which you just plug in a number for the button. And this is kind of useful if you're using anything besides an Xbox controller. Okay, so I want to talk about how to best use controller input, because I know a lot of teams struggle with this. So I'm going to show you our control layout for 2020, and I know it looks a little complicated, but most of the buttons on here are barely ever used. Here's our control layout, and basically what we have is we have one thumbstick that the driver used to turn, and then 2 triggers to go forward and back. The rest of the buttons are specific to this year's robot. So the main thing is reduce the number of buttons for a normal cycle. A cycle referring to picking up, driving to, and then shooting for 2020. And in our normal cycle for 2020, we're really only pressing 2 buttons besides the driving controls. There is intake. You go press intake. It spins up the intake. You pick up 5 balls. It automatically stops. You drive over to shoot, and you press shoot. 2 buttons: intake and shoot. Super simple. Second thing is allow the driver to press buttons ahead of time. So one big thing that's super useful is if you can press a button when you're not really like if you're driving to another place, you're not really in the heat of the moment, you're not stressing a whole lot. So press buttons then when you're like focused and thinking about stuff instead of when you're like trying to do something you're in the heat of the moment. So my favorite example is in 2019, we built an off-season robot with an elevator, and in this game, you would lift hatch panels to different heights. And so when we're driving to get a hatch panel or something, we'd be like, okay, we're going to score high. And obviously you can change this later on, but we'd be like, okay, we're going to score high. I press the button then, and then when you go to place it, you don't have to think. You just press the place button, and it automatically goes to that height. You're not having to like press which height you're at and move your fingers around and a bunch of stuff. It's super simple. The next thing is not necessarily controller based, but don't have locking states. And what I mean by this is always allow the driver to stop what they're doing. So, for example, if the driver was in a state like intaking or shooting, and let's say intaking, it was stuck in intaking, and it was waiting until the last sensor trip to make sure that the hopper was full, and that sensor broke and was always returning false, you would be stuck in intake mode. So we always allow multiple ways to get out of the state. When you press intake, you can press the button again to stop intaking. By far, my favorite button that we implemented a couple years ago is the idle button. And this button, no matter what you're doing, intake, shooting, climbing, doing the control panel, you press idle and it quits that, and it just goes to the idle state of the robot. This is super useful because it's just kind of like default now. You just press idle button whenever you want to quit what you're doing, and it just never gets you stuck in any state. Okay, this is one I see a lot of teams get struggle with is put the most used buttons in the most successful areas. The least used buttons should go in the least successful areas. Talk to your drivers about this, about where is easy to press. So for our specific control layout, I know it's different for everyone. The driver uses his left thumb on the x-axis for the turning, and then he uses his left pointer finger on the trigger and his right pointer finger on the other trigger, and then his right thumb is used to press all the other buttons. And you might use your right thumb to press the D-pad, but sometimes, usually it's, you have to move your right thumb over here, which is kind of annoying. So the most pressed buttons are right in this area, the least pressed kind of tend over here. So intake and shooting, most common, right here. And then less common things like setting the paneler or the control panel mechanism mode to rotation or position, or shooting the target to low or high. Things you barely ever press, so the driver kind of has to work around to get to there, but the most common things are right here. Okay, that's it for the class. We'll send out a quick assignment for this. I know it wasn't the most interesting lesson and this didn't focus as much on code stuff, but next meeting we'll be talking about vision, and that'll be super interesting. And so next meeting is Monday, June 29th at 2 p.m.